In this video, we're going to go over section 7.2 from our textbook, which is on partial derivatives. So bringing it back to the example that we saw in section 7.1, for the company that produced two types of boards, a standard model and a competition model, the cost function was given by this guy here. So if we wanted to differentiate this with respect to x, holding y fixed, and denote the resulting function by c sub x, or suppose we differentiate with respect to y, and then in this case holding x fixed, we would denote the resulting function by c sub y. Differentiating in these ways here, we would obtain this guy here and this guy here. And each of these functions is called a partial derivative. And in this case, each example represents a marginal cost. Remember, if we want to take the marginal, or if we want to find the marginal cost, we would just take the derivative of our cost function. So essentially what's happening here, looking at c sub x here, we're taking the derivative of this guy with respect to x. So we know that when we want to take the derivative of this, we can look at the derivative of each of these guys here. So for example, the derivative of 700 with respect to x is just going to be 0. It's a constant. There's no x term here. The derivative of 70x with respect to x is just going to be 70. Using our power rule here, our x will go away. And then taking the derivative of 100y with respect to x, well, there's no x variable here. So when we say hold y fixed, we're essentially treating this term with the y here as a constant. So y is a constant. Since there's no x variable here, this means that this is also equal to 0. So the derivative of this guy with respect to x just leaves us with 70. Similarly, taking the derivative of this with respect to y, in this case we treat x as a constant. So we know this is going to be 0. There's no y variable here. X is a constant, so this is going to be 0. There's no y variable here. Since we do have a y variable here, we know that the derivative of this with respect to y will be 100. So in general, if z is this function here, then the partial derivative of f with respect to x is denoted by these guys here. These are all equivalent, and it's defined by this limit that we're familiar with here. Similarly, the partial derivative of f with respect to y, with these equivalent notations here, is defined by this limit that we're familiar with here. So let's look at some examples of this here. Suppose we're given this equation and we want to find the partial derivative of z here with respect to y. That's what that notation means. We can also write this as f sub y. Since our function is f here, we want to find the derivative of it with respect to y. So doing so, this term here, 2x squared, that's going to be a constant since x is a constant, so that's 0. This guy here, we treat 3 and x as a constant, so this will just be minus 3x squared times y. Taking the derivative of a constant times y, we're just left with that constant. So we'll get negative 3x squared. Similarly, taking the derivative of 5y, 5 is a constant, taking the derivative of this, we're just left with that constant. So that would be our partial derivative of z with respect to y. Now, if we want to evaluate f of y at 2, 3, what we're doing is we're plugging in our value for x is 2 and our value for y is 3. In this case, we don't have a y term here, but that's fine. Plugging in our value for x here, get negative 3 times 4, which is negative 12 plus 5, so this will be negative 7. Alright, let's look at another example here. We're going to find the partial derivative, but in this case using the chain rule, so it's a little more complicated. For a here, we want to find the partial derivative of z here with respect to y. We have a composition of functions. We know we're going to use the chain rule here. So we're going to take the derivative of this outside function. So we'll bring this 5 down in front using our power rule. And it'll be the derivative of our outside function evaluated at our inside function. And then to the 4th power using our power rule. Then we want to multiply it by the derivative of our inside function. and the derivative of our inside function with respect to y. So again, this x squared term here is a constant, so that's 0. Then we have this 2 times x times y here. Well, 2x is a constant, so we're multiplying just by 2x here. The derivative of 2xy with respect to y is 2x. Multiplying our 5 and our 2x, we'll get 10x times x squared plus 2xy to the 4th power. And so that'll be our partial derivative of this function with respect to y. Doing part B here, we want to find the partial derivative of this with respect to x and then evaluate it at 1, 0. So the first thing we'll do is find the partial derivative of our function with respect to x. We're again going to use our power rule here. So we're going to have 5x squared plus 2xy to the 4th power. Then using our chain rule, we know we're going to multiply it by the derivative of our inside function with respect to x. So we'll get 2x here using our power rule. In this case, we have 2xy. 2 and y are constants, so that means we're going to be left with 2y. Now evaluating this at this point here, so plugging in 1 for x and 0 for y, we'll end up with 5 times 2, which is going to be 10. All right, let's look at another example with a given profit function. So remember our surfboard example from section 7.1, we found that the profit function was given by this guy here. We want to find the partial derivative of y with, the partial derivative of p with respect to y, evaluated at this here, and the partial derivative of p with respect to y, evaluated at this here. So the first thing we need to do is find the partial derivative of our profit function with respect to y. So we know that x is going to be fixed, it's going to be a constant. The derivative of 140x, that's just going to be 0 because this whole thing is a constant. The derivative of 200y with respect to y is going to be 200. Similarly, minus 4x squared is a constant, that'll be 0. 2x is a constant here, 2xy. So our derivative is going to be 2x for that guy. Then we have minus 12y squared, so we'll use power rule on this guy. Bringing the 2 down, we'll get 24y. And then the derivative of minus 700 with respect to y is going to be 0 because that's a constant. And then we can just evaluate these guys. So x will be 25 and y is 10. Here we'll get 200 plus 50 minus 240. And so this will be 10 here. All right. We also want to evaluate this here. So in this case, we're going to plug in 25 for x again, but 15 for y. So we still have our 200 here and our 50 here, and then we're subtracting out 360. So our answer is negative 110 here. All right, so now we want to interpret these results here. So remember, we're taking the partial derivative of our profit function with respect to y here, and remember, y represented our competition boards and x represented our standard boards. So what this information here tells us is that at a production level of 25 standard and 10 competition boards per week, increasing the production of the competition boards, since we took the partial derivative of this with respect to y, our competition boards, increasing this by 1 unit and holding the production of our standard board fixed at 25 here will increase profit by approximately $10 here. And on the other hand, we found that at a production level of 15 competition boards here, increasing the production of our competition boards by 1 unit and holding the production of the standard boards fixed at 25 here will actually decrease our profit by approximately $110 here. Okay? So we are talking about dollars here. All right, so the last thing we're going to look at in this section is second order partial derivatives. So this function z here has two first order partial derivatives like we've seen. We can take the derivative of this with respect to x and we'll get this here, and then the derivative of this with respect to y and we'll get this here. Now each one of these partial derivatives has two partial derivatives called second order partial derivatives of our function here. So remember from previous sections, if we want to take the second derivative of a function, we're just taking the derivative of the derivative. So same idea here, but now for each one of these, we can take the derivative of this partial derivative with respect to x and y, and we can take the partial derivative of this partial derivative with respect to x and y. For example here, the four second order partial derivatives of this function here are laid out here. So here we have f sub xx, and what this means is we're taking the second order partial derivative of our function f with respect to x twice. So that's exactly what we'll do. We take the partial derivative of our function with respect to x, then take the partial derivative of that result with respect to x here. Similarly, we can take the second order partial derivative of f here, first with respect to x and then with respect to y. So we'll do it in that order. We'll take the partial derivative of our function with respect to x first, then with respect to y here. Similarly, we want to take the second order partial derivative of our function first with respect to y, then x. We would first take the partial derivative of our function with respect to y, and then with x here. Now notice, these guys are actually the same. We end up with the same end result by taking these second order partial derivatives. And then lastly, we can take the second order partial derivative of our function with respect to y twice here. So we just take the partial derivative of our function with respect to y, and then with y again. So let's look at some examples of this here. Here are the formal definitions laid out here, but that's the same that we see here. All right, and just make sure that you're comfortable with this notation as well. We'll kind of be using them interchangeably. So let's look at these examples here. We're given this function z here, and we first want to find the second order partial derivative of this, first with respect to x and then y. Right? Going back to our definition here, this is the second order partial derivative of our function with respect to x and then y here. So we're going to use this notation. So for a, we're going to take the derivative of our function with respect to x and then take the partial derivative of that with respect to y. So the derivative of this guy with respect to x here, we're going to use power rule here, so we'll get 3x squared times y. Y is just a constant. Y is also a constant here, so that means this is going to go to 0, and this is a constant, so that'll be 0 as well. So the partial derivative of our function with respect to x is just going to be 3x squared times y. Now we want to take the partial derivative of this guy with respect to y. And in this case, what we're going to do here is treat x as our constant. So this means this guy is just going to be equal to x squared. Similarly, let's look at b here. We want to take the partial derivative of this with respect to y twice. So we're going to take the partial derivative of our function with respect to y, and then do it again. So the partial derivative of this with respect to y here, x cubed, or x is a constant, so this x cubed here is going to be a constant. So we just have x cubed. Then we're going to use our power rule here. So this 4 will come down in front. We'll have minus 8, and then y cubed here. Then we want to take the partial derivative of this with respect to y again. So x is a constant, so this is going to be equal to 0. Then here we'll use power rule, so this 3 will come down in front. So we'll get negative 24 y squared. All right, let's look at C now. We're using slightly different notation. We're going to take the second order partial derivative of this with respect to x, then y, and then evaluate that at 2 and 3. So this, first we'll find the second order partial derivatives. So we're going to take the partial derivative of our function with respect to x and then with respect to y. We actually know from part A here that doing that, we're just going to get 3x squared. So this tells us that if we evaluate that at 2, 3 here, we're just going to plug in this value for x. So we'll get 3 times 4, which is equal to 12. All right, check box all of these. And then the last one we're going to look at is D here. Again, we want to take the second order partial derivative and then evaluate it here. But now we're going to take it with respect to y and then x. All right, so taking the partial derivative of our function with respect to y, we saw from part B here that it's equal to this. Now we want to take the partial derivative of this with respect to x. So using the power rule, we'll get 3x squared here, and then y is just a constant, so this is going to be 0. So now evaluating this at this here, we again will get 12. Alright, so that'll be it for this video.